Hello all. In this video, we are going to see the solution for the GATE Aerospace 2024 exam. The topic that we are going to see the solution is aircraft performance. Without further delay, let's get into the solution. The first question that is given in the GATE 2024 is, which one of the following figure that represents the drag polar of a general aviation aircraft? So it's very easy. So as we have seen in the class, so the drag polar equation is CD is equal to CD naught plus K CL square, where we all know that CD naught is the profile drag coefficient. Okay, CD naught is the profiled drag coefficient, and KCL square altogether it's called induced drag coefficient. Induced drag coefficient. Now if you see here, right, the graph clearly tells. So from this equation we clearly know that the CD, even the CL is 0, the induced drag can be 0, but the total CD will not be 0 because the profile drag will always contribute to it. So wherever the graph in the given options, if you see both your CL and CD are equal to 0, that's wrong. Because if you see this equation, even when CL is equal to 0, CD is going to some value, have some value, right, which is CD naught, which is the profile drag. So obviously option A is wrong, because at this point it clearly tells that your CD and CL, both of them are 0. That's wrong. Then now if you come to option D, that is also wrong. At this point, the graph is in this point, origin, which is your CL and CD is looks to be 0. That's also wrong. Now coming to option B, right? Here it is clearly telling that there is some CL value, which is here, but at that corresponding CL value, the CD value is 0. That is also not possible, right? If there is a CL value, then obviously there should be a CD value, right? Because CD is combination of profile drag as well as induced drag. So whenever there is a CL value, obviously you will get induced drag. So here this graph says that there is some CL value, but there is no CD value. So this is also wrong. So this is the correct profile. Even if you plot this using any of the plotting tools also, you will get the graph of this shape only. So this is the right answer. Option C is the right answer, because it clearly tells that even when your CL is 0, you got certain CD. That is nothing but this. This is called your CD naught, this distance, right? Rest all, as your CL increases, your total CL increases. You see here it is increasing, and as CL keep on increasing, CD will also keep on increasing. When CL is equal to 0, the initial part is CD naught. So option C is the right answer. Now coming to this question, which of the following statements about the general aviation aircraft while operating at a point Q in Venn diagram are true? So it's a very interesting question, because they have given the Venn diagram. So velocity and N is nothing but load factor. We all know, right? Load factor, and the formula for load factor is lift divided by weight of the aircraft at any given point of time. What they are telling is it is operating at a point Q in the Venn diagram. So the aircraft is operating at this point Q, which means what? It is operating at a very minimal velocity. You see here the point that is corresponding to Q is very minimal velocity. So if the aircraft needs to be airborne at a minimum speed, then the aircraft has to fly at CL max condition. Then only it can have maximum load factor, right? Because your L is dependent on your CL as well, whereas you are flying at a very low velocity. So you have to fly at a very high CL max, then only you can able to be airborne, right? So the aircraft is operating at a CL max condition. That is true. Okay, this statement is right. Now coming to the second statement, the aircraft has a highest turn rate. What do you mean by that? How fast or how quickly the aircraft can take a turn. That's called turn rate. Okay, so the formula for turn rate is denoted as omega, which is equal to g into root of n square minus 1 divided by v. This is what we have derived in the class. Given your load factor is fixed, right? which is you are operating at a Q, your load factor is fixed, and you are also operating at a very low velocity, obviously you will have a, because velocity is in the bottom, obviously you will have a higher tan rate, right? Because V is in the bottom and we are flying at a very V minimum, right? You are flying at a very low, because we can still fly somewhere here, but from the question it is given that it is flying in the skew point. So V is minimum. So obviously, which implies that omega, which is the tan rate, will be maximum. So the aircraft has the highest tan rate. That statement is also right. Now coming to option C, the aircraft is flying with minimum drag. That is a wrong statement. I will tell you why. The aircraft can only fly at a minimum drag when it flies at CL by CD max condition. Okay, the aircraft can fly only at a minimum drag when it is flying at CL by CD max condition. But we already know that the aircraft is flying at a CL max condition from the first statement, right? Because it is flying at very low speed, so it has to be airborne, so it flies at a maximum CL to provide sufficient lift, right? So this is the wrong statement. Option D is the aircraft has a smaller turn radius. What is the turn radius formula? R is equal to V by omega, velocity divided by turn radius. So if you substitute that, V divided by omega, you know, right? G into root of n square minus 1 into V, so it becomes V square. So now, since your V is very, very small, right? Because you are flying at a minimum speed here. You see here, this region. So obviously the radius of turn will also be less. So as V is minimum, which implies that turning radius of the aircraft will also be small. So that the aircraft has the smallest turning radius. So option A, B, and D, all three are the correct statements. Moving on to the next question, which is an interesting question. A similar kind of question is also asked in GATE 2015, correct? But that time they asked the expression directly, but this time they just asked how it is varying, whether it is linearly or exponentially or increasing or decreasing, like that they have asked. From the question which is given here, we have clearly know that they have asked the density variation versus altitude. So density versus altitude h at isothermal region. What is isothermal region? No temperature change. Temperature is equal to constant, right? Temperature is equal to constant. So we have multiple regions in atmospheres, or multiple layers like troposphere, stratosphere, mesosphere, exosphere, ionosphere. In that, the region where temperature is constant, which is an isothermal region, is nothing but stratosphere. Stratosphere implies temperature is equal to constant. So which is an isothermal region. Okay. Now they asked in the stratosphere region how the density is varying with respect to altitude. So we all know that till 0 to 0 altitude, from the sea level till 11 kilometer, it is troposphere, right? Troposphere. And from 11 to 25, it is stratosphere. So this region is stratosphere. But then they have asked how does the density is going to vary in this 11 to 25 kilometer range. So we know that all the expressions that we have studied in the books are related to troposphere. Now we have to derive the expression that are related to stratosphere. It's very easy. As we have seen in the class, the atmospheric relationship has been derived from Pascal's law, hydrostatic law basically. So P is equal to minus rho G dH. Basically dP, change in pressure, is equal to minus rho GDH. So now we want the density variation here. So what we have to do is, we know from ideal gas equation P is equal to rho R T. So from here we can, instead of P we can directly substitute D into rho RT equal to minus rho G dH. Since it is an isothermal region, stratosphere region, your temperature is constant. So R and T you can treat to be constant, you can take out of the delta. So d rho by rho equal to minus G by RT into dH. See, we have taken R and T as constant, especially T as constant because it's an isothermal region, because the questions they have clearly asked us an isothermal region, so temperature can be treated as constant. If it's a troposphere, temperature cannot be treated as constant. Okay, that we have already seen all these things in the class. So d rho by rho equal to minus G by RT into dH. Now if you, let's do the integration, very simple integration. D rho by rho is ln rho, and you can put, if you know the sea level to be 0 and variation to be 1, you can keep like that. And then here minus G by RT into H. H also you put sea level to be 0 and unknown H to be H. And if you substitute your equation, it is ln rho 1 by rho naught is equal to minus G by RT into H1 minus H naught. And if you cancel log, it will become rho 1 by rho naught is equal to e power minus G by RT into H1 minus H naught, right? So it's rho 1 is your density variation in the stratosphere. Rho naught is nothing but your known temperature. It could be sea level or whatever it is. It's a known temperature, right? Or maybe the base of the stratosphere, which is your tropopause. So it is clearly telling that your temperature is varying exponentially, but since there is a negative sign here, it is decreasing exponentially. It is not increasing, it is decreasing exponentially. So this is the rate or the expression at which the density is varying at stratosphere. This expression will not be true for troposphere, because in troposphere we don't treat temperature as constant here. Here we will treat temperature as constant. Okay, so it is exponentially decreasing. So option C is the right answer, decreases exponentially. Now, which of the following statement about the absolute ceiling and service ceiling for a piston propelled aircraft are correct? So they have given a lot of statements about the absolute ceiling and service ceilings of the piston propelled aircraft. Now we have to figure out what is right. At service ceiling, the maximum rate of climb is 50 feet per minute. Actually, at service ceiling, the maximum rate of climb is 100 feet per minute. Okay, but in the question it is given that it is 50 feet per minute, so it is not the right statement, so it's a wrong statement. The altitude corresponding to absolute ceiling is lower than the service ceiling. This is also wrong, because always first comes service ceiling, where the aircraft can fly, still comfortably fly. Next only it comes absolute ceiling. For example, if the service ceiling is, let's say 30,000 feet, maybe absolute ceiling will be 40,000 feet. I'm just putting some numbers, okay? So always service ceiling is at lower altitude compared to the absolute ceiling, because service ceiling is where you are allowed to fly. Absolute ceiling is where you will not have any excess power. The power that is required by the aircraft will be the available maximum power. So hence we will always fly at service ceiling. So this statement is also wrong. The altitude corresponding to absolute ceiling is lower than that of service ceiling. It is given like that, but actually service ceiling is lower than that of absolute ceiling. So this is also wrong. Coming to option C, at the absolute ceiling, the power required for the cruise equals to the maximum power of available. Yes, that's true. Because at the absolute ceiling, we know that the rate of climb, right, R by C is equal to 0. Because there won't be any excess power. At absolute ceiling, the rate of climb is 0 because there won't be any excess power. What is excess power? Power required minus power available. So here hit, because in absolute ceiling the power required will be equal to the maximum power available. So this is the right statement. The altitude corresponding to the absolute ceiling is higher than that of service ceiling. Yes, that is also true, because absolute ceiling will always be at higher altitude compared to service ceiling. So the right statements are C, option C and option D. Okay. Yes. For an aircraft moving at a 4 kilometer altitude above the mean sea level at a Mach number of 0.2. So they have the given information is uh, an aircraft which is moving at a Mach number of 0.2 and the altitude at which it is moving is equal to 4 kilometer. Okay, great. What they are asking is the ratio of equivalent airspeed to true airspeed. The ratio of equivalent airspeed to true airspeed. It's a very straightforward problem. So we have already studied in the class, and we have derived also the formula for true airspeed and versus equivalent airspeed, right? So V equivalent VEAS divided by VTAS, equivalent airspeed and true airspeed, is nothing but, this is what asked in the question, ratio of equivalent airspeed root of rho by rho naught, where rho is the density at that corresponding altitude, rho naught is density at sea level. Okay, so in the question it's also clearly given that rho naught density at sea level is 1.225. It's clearly given. Similarly, rho at altitude, which is in this case the altitude is 4 kilometer altitude, that is also clearly given in the question, 0.8219 kg per meter cube, and this is also kg per meter cube. Okay, so square root of 0.819 divided by 1.225, which is nothing but square root of 0.668571, and if you take the square root of that you will get 0.817. In the question is asked that round off to 2 decimal places, so which is equal to 0.82. So the ratio of equivalent airspeed to true airspeed is 0.82 is the right answer. And it makes sense also, right? Because we always know that the equivalent airspeed will always be less than the true airspeed. The actual flying speed of the aircraft is always higher than the equivalent speed of the aircraft. So that's the reason the equivalent airspeed divided by true airspeed is coming out to be less than 1, which makes sense. Okay, and this is the last question in the aircraft performance. It's a very easy question. An aircraft experiences a net vertical ground reaction of 15,000 meters. So they have put that net vertical ground reaction, sigma summation of Fi is equal to 15,000 Newton. Okay, and the weight of the airplane is also given, which is equal to 10,000 Newton. The landing vertical load factor defined as the ratio of inertial load to the weight of the aircraft is. So the load factor is very simple. The net vertical load which is acting on the aircraft divided by weight of the aircraft. So the net vertical load is nothing but sigma Fi. We don't need to calculate the net vertical load. What is that, this and all. Everything is already calculated. They have clearly given the net vertical ground reaction. By the time it lands the aircraft lands the ground reaction is 15,000. So that's the net vertical force. Divided by weight is the load factor. So 15,000 divided by 10,000, and the answer is 1.5. So the load factor is 1.5. Yeah, with this we have solved all the GATE 2024 aerospace questions. related to aircraft performance. Okay, to know more these kind of concepts and get started with your aerospace career, to know about the aircraft industry, how do they operate, what are the skill sets that you develop in the aircraft industry directly from industrial experts and academicians and everything, to crack GATE and all those things, and also to find out different opportunities through GATE, please join the JNF Academy. Thank you.